Hello everyone, welcome to the sixth webinar of our webinar series about microseismic and geomechanics. So today's speaker is Devin Garrett. He is involved in developing the induced seismicity and microseismic tools here at IMaGE. So before joining IMaGE, Devin was a microseismic specialist for SLAMAGE and ESG solutions, focusing on both induced seismicity and downhole projects. So he has lots of experience from the field to share. In this webinar, he'll share with us with his experience in induced seismicity monitoring. So, Devin?
All right, thanks, Jinwei. As Jinwei mentioned, my name is Devin Garrett, and I'll be giving this webinar talk on induced seismicity monitoring. I believe it's the sixth part in this series that IMaGE is putting together, so here we go without further delay. I'll just go over a quick outline of this webinar here. We'll review the previous ones just in case anybody hasn't watched them. They can know what they can go back and watch. And then we'll talk about what is induced seismicity and why we're concerned with it. And from these concerns, some regulations have appeared in different areas, so I'll talk about some of them. And for these regulations, we'll talk about how it's monitored, what equipment we're using, and the processing methods that we're using here at IMaGE, and generally what people use to process it. And then we'll wrap it up with some examples and case studies. And that's it. Yeah, so as I mentioned, this is the sixth webinar in this series. The previous webinars have covered areas such as survey design and project setup. Then we get data acquisition and triggering and processing and QC, as well as some interpretation. So I won't go into much details about those topics here, but I believe they're available through our website or through our YouTube channel. If you want to go and learn more and you haven't seen those webinars yet, I encourage you to go and view them. So what is induced seismicity? So in the past several years, there have been lots of headlines in the news talking about induced seismicity and earthquakes generated from fracking or wastewater disposal wells throughout North America and the world. But these earthquakes and induced seismicity aren't just part of oil and gas industry. They're also associated with a lot of other industries, such as CO2 storage or dams, even geothermal applications, and mining all have induced seismicity associated with them. So it's been a hot topic in the news. You always see the buzzline, induced seismicity. And what it's really referring to are seismic events that are a direct result of human activity. So this is just any earthquake or seismic event, doesn't matter the magnitude, that is caused from human activity, whether it's fracking or mining or the creation of a dam or anything. What it is not referring to are naturally occurring earthquakes that are typically located on tectonic boundaries. So just the human activity part. This is a map kind of showing where in the world it's happened, and as you can see, it's spread throughout the world pretty much. You know, there's a large concentration in North America where we get a lot of headlines from, but also in Europe there's a bunch, and Asia, and even down in South Africa. In this map you can also see that they're colored by the different causes. So I'll talk mostly about oil and gas induced seismicity today, but the principles will apply to all these other causes as well. But typically, you know, oil and gas, we're seeing a lot of them in North America, especially in central United States, but they are also present in Europe and a couple in Asia. Whereas mining induced seismicity, we get a lot in Asia and South Africa, but there's still some in Europe and in the eastern United States, so worldwide. And even things like geothermal energy, we're getting a lot of those in Europe and even up in Iceland too. So the cause can be anything, and they can occur throughout the world. The circles here represent the magnitudes. So we're getting events from as low as magnitude 3 or lower, which are hard to be detected in some cases, but all the way up to magnitudes 4 and 5. So something that is, so events that are quite large and concerning to a lot of people. And it's really some of these larger magnitude events and the frequency of them that they are occurring at that's got a lot of people concerned. So to lead into that, why is it becoming such a hot topic today, and why is it in the news so often? Why is everybody concerned about induced seismicity? This is a plot generated by the USGS showing the number of earthquakes in the central and eastern United States from about 1975 until 2015. And so for the first 30 or 35 years of this plot, you can see the blue line. It's a pretty steady rate of earthquakes, and they were generating about 25 earthquakes per year of magnitude 3 or greater. And looking at the map, these were scattered throughout the central and eastern United States. So it wasn't really heavily confined to one area. There were a couple areas with more than others, but in general it was all over the place. But since 2008 or 9, the number of earthquakes per year has grown exponentially to the point now that we're getting 500 or 600 earthquakes per year of magnitude 3 or greater in this area. So the fact that we're getting significantly more earthquakes per time frame is a huge concern. Additionally, a lot of them are being concentrated in one small area here in Oklahoma, and so a lot of the concentrations of these induced seismicity is really being in small areas that have people concerned. So this increase in the number of earthquakes happening every year obviously is a major worry to people, and especially when we start getting larger magnitude earthquakes that cause damage. So this is a picture of a road in Oklahoma where an earthquake has obviously done some damage and needs some repair. But it's not just things like roads and public structures, it's also damaging houses. This one is in Texas, I believe, where part of the chimney has fallen down. So some of these larger earthquakes are causing damage. They could be more annoyances, such as in this store. This is in Tulsa, Oklahoma, where all it's done is knocked items off of shelves. This has also happened in people's homes throughout North America as well from some of the smaller earthquakes. So not necessarily doing damage to properties or anything, but still potentially breaking small items or at the very least causing a mess. And some extreme cases can do a whole lot of destruction. So this is an earthquake that was deemed caused by a reservoir in China of magnitude 7. So a lot of damage can be done by these induced seismic events, and a lot of this is why there's so much concern today. The public and governments are all worried about the amount of damage that these can do, and if they're occurring more frequently, there's a rise in concern. So as a result of this increased seismicity, there's been several government bodies that have put out some regulations. And again, I'm going to focus mostly on kind of oil and gas related ones, but there are definitely some associated with mining and geothermal and other industries as well. So some of these include the UK, parts of the USA and parts of Canada, which have regional monitoring requirements for any hydraulic fracturing or wastewater disposal. And these regulations can typically come in two main types so far. The most common by far, and what most people are probably familiar with, are traffic light protocols. So this schematic here on the right is an example of the Alberta traffic light protocol. And I'll just give a quick kind of walkthrough about it for anybody who's not familiar. So for this type of regulation, operators are required to do real-time monitoring and processing of events to generate the magnitude level of each event in real time. So as they are fracking or disposing of wastewater, if they're generating events of less than magnitude 2, it's deemed safe and okay in this area, and they can proceed as they were doing, as operating. However, it's as soon as they start seeing events of greater than magnitude 2 and less than 4 that we move into this yellow light region. And at this point, the operators need to, first of all, inform the regulatory body, but they also need to invoke their response plan, which was in place before the start of operations. So this response plan is going to be unique to each operator and can vary from reducing the rate or the volume to taking longer breaks in between stages or skipping stages entirely. But if it is this yellow region, the operators are still allowed to proceed. They just have to proceed with caution and maybe at a lower volume or rate or something than they were originally doing. And then in this case, for this traffic light scenario, if they get a seismic event of magnitude 4 or greater, then everything has got to be shut down, and the operator has to consult with the regulatory body before being able to resume operations. So again, this is just an example of a traffic light protocol. There are several areas such as the UK that have implemented them, maybe with different, or I know with different magnitude levels for the thresholds, but it's the same general principle. As long as we're seeing small magnitude events, everything's fine and they can proceed as planned. But as they move up into higher ranges, then some response plans need to be initiated. And if they get above a certain magnitude, then everything has to be shut down for a period. The other common type of regulation is it's a non-real-time solution, and this just requires some ground motion monitoring. So for example, northeastern BC has an area where they need to just place an accelerometer within 3 kilometers of a treatment well, and this pad will not be monitored in real time, so any induced seismic events that occur while treatment will just continue to go right on. But after the fact, the data from this accelerometer will be processed, and the information will be handed into the regulatory body for any events that exceed a certain threshold. So for northeastern BC, for example, that threshold is 2% of G. So these kind of operations and regulations, they don't have any firm situation where they will be shut down or forced to monitor or modify, their operation treatment. But that's not to say that the regulatory body isn't watching their own network of sensors, and if they see a large magnitude event, they may still contact the operator and ask them to stop or to change their injection treatment plan. So as a result of these regulations, and also because of the overall public perception of induced seismicity, most operating companies are extremely concerned with induced seismicity and trying to minimize the occurrence of it, and especially the larger magnitude events. So in general, everybody's concerned, whether it be the public, the government body, and operators. Everybody's concerned about it and wanting to minimize it and minimize the damage that can be done from induced seismicity. So now that we know the general types of regulations out there, I'll talk a bit about the equipment that's used to monitor and acquire the data for these induced seismicity operations. Typically in the field, we'll have either broadband seismometers or accelerometers. So here's just an image of kinemetrics instruments. On the top is a broadband seismometer and the bottom is an accelerometer. Now both of these sensors are fairly small. They're only 10 or 15 centimeters across and about that same in height. So not very big to be putting out in the field, so nice and small footprint. But they are designed to get a low enough frequency bandwidth that these larger magnitude events will be detected on both of them. This is a picture of a typical field setup. So in the field, not only do we have, in this situation, we have both an accelerometer and a broadband seismometer deployed. So the broadband seismometer is located right here, and it's just in a very shallow hole, maybe 10 centimeters or so deep, so not deep enough to have to need ground disturbance or anything. and the accelerometer is just mounted on a concrete block that's about a square meter and placed in the field. So again, this is all just dropped off, the day they're setting up. It's really easy to set up in a small footprint there. And aside from the sensors, what we'll need is some electronics such as the power supply, digitizer, and storage disk. And this is typically stored in a box located, a weatherproof box located right next to the sensor. So in this box that our partner Resolve has put out here, they will have batteries to power everything and some kind of method to store the data if necessary. And again, here on the other side of this white panel here are solar panels to charge the batteries, so it's all a self-contained unit. And for real-time operations, we can see an antenna sticking up, and that's used to transmit data back to the central server here in Calgary to be processed. So all in all, it's a very small footprint. Each station can be easily set up in a matter of a couple hours kind of thing once we know where it's going. So it doesn't need a lot of leadway before the frac, although the more time the better. But also once it's after the job, when it's removed, it doesn't leave a big site behind. There's almost no evidence that anything was there. So this is the typical equipment from the field perspective. For the office and the actual processing of the data, it's pretty simple. All you need is a computer with some software that is capable of processing ISM data, such as our Insight suite. It's specifically designed, one of them, for processing ISM data. And again, just to drive home the fact that these are really small instruments that don't require a lot of space in the field, this is, again, a scale. So you can see the broadband seismometer on the left here. Got a power pack and a digitizer in the center, and then a laptop for scale on the right. So it's small equipment, doesn't need a big footprint, and can be easily placed in the field, just a bit away from your frac site to try and reduce any noise generated from that. All right, so I'll go through a couple of scenarios of the workflow for collecting and processing ISM data. So first, we'll talk about real-time alerts, then we'll talk about post-processing workflows. And in both cases, they're pretty similar, but I'll mention the differences later. So here on the left, we've got a picture of the field setup I just mentioned. So for any real-time job, we might have 3 or 4 of these stations, or maybe even more, set out in the field, recording data. And this data will be streamed continuously back to our server here in Calgary. And this will be done using cell networks, or if the instrument can be placed near infrastructure or anything, we can use available internet. Either way, the data will be collected here in Calgary on our server, and Insight will accumulate all of the different sensors and signals and will process and trigger out the data. So more about how to process and trigger the data is covered in previous webinars, so watch those if you have any questions about how that is generally done. But once Insight generates a trigger, so an example of that is seen down here on the bottom, it will process it and locate it and calculate a magnitude if it has multiple stations to do that for. Or if it's just a single accelerometer out there, it will calculate the maximum acceleration. And if either the magnitude or the acceleration value exceeds the threshold set up in the system, this will generate an automated text message or email alert to any interested parties. And so this whole workflow of triggering and sending the alerts is quite quick. And it's just a matter of minutes from when an event actually occurs in the field to receiving a text message or an email alert. It all happens in near real time, just only a couple of minutes of delay. And one of the keys also is that once a trigger is generated, they will all be reviewed by geophysicists here in Calgary to ensure that we are actually seeing a seismic event and it's not just a false positive trigger or some noise kind of thing. So if a truck drove by a sensor, for example, or something, it might generate a false positive. So all the triggers will be manually reviewed to prevent false positives from being sent out. So the non-real-time workflow is very similar to that of the real-time workflow. The only major difference will be that the data will not be continuously streamed to a central server here in Calgary, and will instead just be stored on a USB stick or drive on site. At the end of the job, the stations will be collected, and that data will then be uploaded to our servers here in Calgary, and then the same process will happen where Insight will load and trigger out the data, and all events will be picked and located and manually QC'd, and from there a final report will be generated and delivered to the client, as opposed to text messages or email alerts, because it is not real time. So very similar workflow. The main difference is just whether data is streaming to Calgary in real time or not via cell networks. All right, so now that once we have the data triggered in Calgary, it's a geophysicist such as myself's job to go through the data and ensure that what we're seeing is an actual seismic event and it's not just some noise. So here on the screen I'm showing two example waveforms. Both were identified as triggers from Insight based on threshold levels. And so the top one is a clear seismic event. So this is what we would be looking for. We want to see a nice P arrival, which is identified by the red waveform here. And then a few seconds later, a shear wave arrival, which is the blue waveform. And the fact that they're blue and red signify in Insight that they're orthogonal to each other. So that's what we're looking for in terms of an arrival for an event. Additionally, before and after the event, we'd like to see it nice and quiet, so you can see it's almost flat before and after. So there's not a lot of noise that's affecting this or anything, and this is almost a textbook seismic event to be picked up by Insight. Now you compare that with the bottom sensor or trigger, and we can see right away that it is a much higher frequency waveform, but more importantly, there's no clear separation of a P and shear phase. We kind of see the red channel has got some spikes throughout, but so does the blue channel. And again, it's noisy before anything's arriving and for a while afterwards. So this would be generated by some noise on site, whether it's traffic driving nearby or an animal or wind or some kind of environmental noise or from the earth itself. But this would be something that the processor, the manual QC would catch and would flag as noise and would prevent an automated trigger from, or an automated notification from being sent out, or it would be omitted from the final report kind of thing. So just because Insight can handle all of this and generate triggers automatically, we still need people to QC everything, because Insight can't determine the source, whether it's an actual seismic event or if it's just noise. All right, so now I'll cover a bit of an example case study, I guess. So here we've got 4 treatment wells. You can see drawn in blue here. And around this site, we've placed 5 sensors in 4 stations. So 4 of them were broadband seismometers. And there's also been an accelerometer placed at the same location as one of the broadband seismometers. Prior to actually acquiring any data, one of the main things that we'll do is we'll run a survey design. And again, we've got an entire webinar dedicated to survey design, so I won't go into a lot of detail about that here. I'll encourage you to go back and watch the webinar about that. But really what we want to do is we want to make sure that the setup, all the sensors will monitor and record any seismic event of a certain magnitude. So for this one, you can see that the magnitude threshold for the entire pad is approximately 0.5. or this kind of light blue covers pretty much everything, light to dark blue. And so for this scenario, if our mandatory requirements were to monitor anything, down to a magnitude 1 or 2, this would work. This setup would work. But if the regulations required us to know down to a magnitude 0, obviously this setup would not be sufficient, and we would need to either increase the number of sensors, or maybe move them into a smaller area, or something else to try and increase that detectability. So this is one of the 2 features we'll do in a survey design. The other one is we'll run a Monte Carlo simulation to try and assess the location accuracy. And so again, more information about this in the survey design webinar. But what we're looking for is we want all of the events from a Monte Carlo simulation where we're just varying the picking accuracy and the velocity model accuracy generally to be located in a small area. And that's just to make sure we have fairly good confidence in the real-time results and also final results, to know that the events are happening in the area of the pad, as opposed to potentially being kilometers away. So again, more information about this in previous webinars that I encourage you to watch if you haven't already. So once we've acquired the data, we transmit it back to Calgary, and so here's an image from InSight where it's taken all the 5 individual sensors and amalgamated them into one trace and triggered it out. Again, this is a very high quality waveform, and you can see the P arrivals, the P wave in red, and the shear in blue. So here it's been quite accurately picked by the computer, but it will still be manually reviewed just to ensure that all these picks are good. Additionally, you can see the difference between an accelerometer, which is this middle trace here, and then the 4 broadband seismometers are the 2 above and 2 below. The accelerometer has a larger frequency response window, so you can see a bit more high frequency in the data from that sensor. So, but they are all capable of detecting the larger magnitude events that are associated with induced seismicity. So for this particular case study, we had over 1,000 events detected, and once they've been triggered out by InSight and located, we can map them out relative to the well bores, as you can see here, and colored, in this case, by time. So if we're able to get this amount of detail, which is fairly standard, having 4 or 5 stations out there, you can start to identify some lineations and structures that are being activated by your treatment. So in this case, you can see there's a lot of northeast to southwest structures that are being activated, and generally they are growing from the northeast to the southwest, and that's likely because we're treating the wells from north to south in this situation. But you can also see which way things are growing, and you can anticipate when a lineation will cross the next well bore. So not only are we able to color them by time, but we can color them by well, as you can see here. So anything that's colored yellow, for example, was the event happened while treating this second well here. So we can see that we get events crossing all the way down into this well 3 area. Not a lot of growth back towards well 1, so it's mostly down towards the southwest. We are also able to color them by stage. I haven't shown it here, but we can break it down even further if we want to know exactly which stage of treatment is being affected in which area. And we can color them by magnitude, as shown here, or several other parameters that I won't go into too much detail, but pretty much any parameter you can color microseismic results by. We can also do induced seismicity. But here, yeah, we can just see where the larger magnitudes events are happening, and identify that this one main structure has a lot of the large magnitude events. In this case, the largest magnitude event was at 2.8 and happened right down there. But another very useful visualization. So finally, for any project that we've got a handful of sensors out there and they have a large azimuthal spread to them, we can do some advanced analysis, not in real time, but after the fact, to get some moment tensor solutions or some fault plane solutions, as you can see here. So here we've plotted up the fault plane solutions of a handful of the larger magnitude events that we detected on this project. And you can see that typically they're all, striking approximately 255 degrees in this scenario. So any project that we have 4 or 5 stations put out there, we can, if the signal's strong enough, we should be able to go in and get some moment tensor and fault plane solutions for some advanced analysis information. So now I'll switch up a bit and talk about the other type of monitoring where maybe it's only required to have a single accelerometer out there. And this is more to just get the absolute ground motion value or acceleration value. And so from this, we're only going to have one trace of data. And an example of that is here. And this one hasn't been rotated to the PNS wave component, so the colors don't necessarily match that. But you can see the onset of the first arrival here is the P wave that's being picked by the blue line. And then we get, goes a little bit stronger, and then the shear wave really arrives here where the green is onset. So from this, the main deliverable we'll get is being able to calculate the peak ground motion or the peak acceleration value. And that will be independent of any picks. It'll just be in this trigger, the peak acceleration value is the value. But another thing that we can try and estimate doing is we can estimate a magnitude based on the response of the signal and the PNS separation. We won't be able to get an absolute location or an absolute magnitude because the magnitude is dependent on location. To some degree. So we can just get an estimate of the distance from the accelerometer and try and estimate the magnitude, but definitely a lot less information that we can get from only having one sensor or one accelerometer in the field as opposed to a network of 4 or 5. All right, so for both projects, whether it's a network of 4 or 5 sensors or just a single sensor out in the field, we'll also analyze the background noise after the project. If we have time before, we'll do that beforehand too. But this is just to ensure that the sensors will or would have detected any events above the threshold that is required. So for example, in this case, we've got 2 plots of the RMS signal for one project, and in the top we can see it was during pumping, and the bottom was before pumping had started. But in both cases, the average background noise was only 0.1% G during pumping, or 0.05% G before pumping. So in both cases, it's much less than the threshold of 2% G. So it gives us good knowledge that we would have detected any event had there been anything above a 2% G, and nothing would be missed. All right, so that about wraps it up from induced seismicity. So thanks for listening. Just a few conclusions here. It is being mandatory to monitor it for several different areas within Canada, the US, the UK, and more, I'm sure. And typically the traffic light system is probably the most commonly used requirement, where you need to do some real-time monitoring and magnitude level notice of the events. But there are some places that are using just some post-processing information, such as the peak ground acceleration. For both these, broadband seismometers or accelerometers are used. If you need acceleration, accelerometers have to be used. But they're fairly similar instruments, similar footprint, and the setup in the field is quite similar and easy to do. And both can have real-time or non-real-time solutions. to be used. And if you want any advanced analysis, such as fault planes or moment tensor inversions, then a complete network of 4 or 5 stations at the minimum would need to be set up for processing. All right. I also mentioned that we've got one more webinar at least coming up on microseismic geomechanics, and this will be in October at some point. So stay tuned for the announcement of that one. And thanks for listening. If you have any questions, I'd be happy to answer them.